The duality between motion planning and approximate inference is well known. Here we can interpret the optimization problem as performing maximum a posteriori inference over the space of trajectories, where the mode of the distribution corresponds to the lowest cost solution. Map inference requires the definition of a likelihood probability and a trajectory prior. One prominent example of this paradigm is Gaussian process motion planning, or GPMP. A prior over trajectories is defined as a Gaussian process, which encodes smooth system dynamics. Continuous trajectories are parameterized by a discrete set of support states denoted by theta. However, the posterior distribution may be multimodal, often due to a non-convex cost function, such as the presence of obstacles. In this case, we can define a variational inference objective to capture relevant modes. This seeks to approximate the entire posterior distribution by minimizing the reverse KL divergence between a proposal distribution Q and the target posterior. This can also be shown to be equivalent to an entropy regularized motion planning problem. Recovering the optimal distribution can provide a source of experts for imitation learning approaches and approximate value functions for model-based RL algorithms. To model the target posterior distribution, we leverage Stein Variational Gradient Descent, or SVGD, a recent nonparametric inference algorithm. Here, the proposal distribution is represented using a set of particles over the parameter space. At each iteration, we evaluate the functional gradient and perform gradient descent to iteratively update the proposal distribution. The particles evolve according to a gradient flow, where particle velocities are governed by maximum and repulsive forces. This drives particles towards regions of high probability, and the repulsive term pushes them apart to avoid mode collapse and promotes particle diversity. Our algorithm, SVGMP, modifies Stein particle gradient descent to account for local geometry in the planning problem. We compute the Hessian for each particle in batch, which is then used to construct a positive definite metric. This allows us to incorporate average curvature into the kernel to scale interparticle distances, and also acts as a preconditioner to the SVGD gradient, resulting in a Gauss-Newton-like update. As in GPMP2, the posterior distribution is represented as a factor graph, with local costs represented as individual unary or binary factors. As a result, the metric is sparse block diagonal and can be efficiently inverted for the update step. We test this approach on a 7 degree of freedom manipulator, where the robot must place the green cup at the red goal while avoiding the 3 obstacles. We initialize the motion plans by randomly sampling from the GP prior and perform iterative updates until convergence. Each particle trajectory is indicated by the corresponding colored end effector trajectory. Green lines signify lower cost trajectories, whereas red denotes higher cost.